we looked at the most generic case, case one, where we talked about that both payments and interest rates can change over time. In this case, we looked at what expected present discounted value would be for the sequence of payments, where we allow both payments and interest rates to change over time. Now I want to discuss case two. Now, case two is payments can still change over time, but interest rates are expected to be constant over time, right? So we're looking at the second case where we still allow payments to change, but we're saying interest rates expected to be constant over time. So that IT, which was the 1 year interest rate from year T to year T plus 1, is equal to IET plus 1, which was expected 1 year interest rate from T plus 1 to T plus 2, is equal to IET plus 2, so on and on till I, right? So we're saying payments can still change over time, but interest rates expected to remain constant. So if we draw the timeline again, time T, which represented today or the present, right? We knew this had the payment $Z, right? This was the payment today. So T represents today or like the current year, right? So this is today. So this is where we want to find the value, right? When you find expected present discounted value today or current year, right? At T plus 1, we have ZT plus 1. This is something that we looked at important already. At T plus 2, we have ZET plus 2, right? This was the payment today. This was the payment a year from now. Was the payment 2 years from now. ZET plus 2 and so on. Right, so now interest rates expected to remain constant. So we know when we're finding expected present discounted value, we're finding the value today, right? So we want to get all of them in terms of year T. Z is already at year T, it's already in today, so we don't need to do anything with that. For this payment, which is a year later, we need to discount it back to today, right? And this is discounted, we know, using IT, which applies from T to T plus 1. But since IT is the same as I, which is discounting it using I. And then we know this payment that is at T plus 2 needs to be first brought to T plus 1. And we typically do this with I T plus 1, which applies from T plus 1 to T plus 2. But since it's equal to I, so this is discounted using I. So this contrasts to part 1. And then once we have it at T plus 1, we need to bring it back to T. We would have done this with IT, which applies from T to T plus 1. But since IT is the same as I, so this is discounted using. So in general, to move from T plus 1 to T, we have to use IT, which applies from T to T plus 1, but here IT is just I. To move from T plus 2 to T plus 1, you will have to use IT plus 1, as that applies from T plus 1 to T plus 2, right? It's a 1 year interest rate in year T plus 1, so it applies from T plus 1 to T plus 2. But over here, IT plus 1 is just I, right? So, and then obviously to move from T plus 1 to T, we use IT, but IT is just equal to I, right? So in this case, expected present discounted value just becomes, okay, let me write it over here. So EPDV, this is the value today, today's year T. So EPDV becomes, in this case, so we write it as this VT. So it's going to be just ZT because it's already in year T, so you don't need to discount it. And then it basically becomes ZET plus 1, which is discounted by 1 plus I, right? So we discount it using, we can discount it using I, so then we just divide it by 1 plus I, and then 1 by 1 plus I squared. Because first you bring this payment to T plus 2 to T plus 1, and then you bring it to T. So it has to be discounted twice, right? $ZET plus 2 and so on. Right. So this is how this case is different from the first one. That was a more generic case. We're using IT plus 1, IT plus 2, depending upon where the payment was, how much discounting it needed. Remember, a payment at year T, when you're finding the value in year T, does not need to be discounted. A payment at T plus 1 need to be discounted by 1 year back to T. A payment at T plus 2 needs to be first brought to T plus 1, then brought to T. And we now looked at this case where payment interest rate is expected to be constant over time, but payments can change. Now let's look at a sub case for this. So let's look at sub case 2.1. Zero interest rates. Zero interest rates. If I is 0, right? If I is zero, right? We're just saying interest rates are expected to be constant over time. What we're saying, what if that constant value is zero? Then 1 by 1 plus I is just 1, right? Because 1 by 1 plus 0 is just 1. And so is 1 by 1 plus I power n is 1 for any power n, right? Whatever power n you take, right? So if we're saying that interest rates are expected to be constant over time, if that constant value is 0, then 1 by 1 plus I is 1 and 1 by 1 plus I power n is also 1, right? Because this is just then 1 by 1 plus 0 power n, which is just 1 by 1 power n, and 1 to the power anything is always 1, right? So this is just 1, right? So this is this. So EPDV in this subcase 2.1 becomes, right? This was pound VT. This is equal to ZT plus ZET. It just becomes this Y. Let's just look at this plus ZET plus 2 and so on. Why? Because we were dividing this by, we were multiplying this by 1 plus I, right? And this 1 plus I is just equal to 1 by 1 plus 0 is just 1. You were doing this 1 plus I power square, which is 1 by 1 plus 0 power square is 1, right? So in case of zero interest rates, so if interest rates are expected to remain constant at this particular value 0, so in case of zero interest rates, expected present discounted value of a sequence of expected payments is just the sum of those expected payments. Is just sum of, so if we're assuming for simplicity, like in any problems in the end of chapter questions, that we have zero interest rates, so that what that implies is that expected present discounted value of a sequence of expected payments is just sum of those expected payments, right? This is the implication. So this simplifies the end of chapter questions a lot when we assume zero interest rate.